Yesterday we did this something and we continue from here. Before we do calculation for capacitance, let's take an example and see the values, kind of values you get for a typical PN junction looping. An example taken is given that for this PN junction is 5 into 10 to the power 18 per cc, then ND given to us is 4.5 10 to the power 15 per cc, and of course as usual Ni square at T is equal to 300 degree Kelvin, 2.25 10 to the power 20 per square. This is square of that. Since I know all of it, I also know dielectric constant, silicon which is 11.8, Q is 1.6 into 10 to the power minus 19, and epsilon 0 is 8.854 or 85 at least, minus 50 rad. So this kind of data will be given to you. We want to know what is the value of W, what is the value of E0, and also V0. This is what we did yesterday. We gone. So let's start moving. How do I calculate V0? I can calculate V0 easily because I have been given dopings Na and Nd. Since I am given a doping Na and Nd, the built-in voltage is known. So first thing I do is V0, and in some books they also call built-in voltage. So maybe some books write VBR, so you can use either way. And then that is kT by Q ln Na in the y Ni square. The assumption here is that at T is equal to 300 degree Kelvin, all donors and acceptors are ionized. That's our assumption. So with this, kT by Q ln, if I substitute this value and assume this to be 25 millivolts, ln 5 into 10 to the power 18 into 4.5 into 10 to the power 15 divided by 2.25 10 to the power 20, 18 plus is 33, this is 22 points into 34 minus 20. So this gives me some number, so 10 to the power whatever it comes. This roughly I get 0.69 V. So if I am given the doping on either side of the junction, I will be evaluating first the built-in voltage, which is kT by Q ln Na and D by Ni square. Once I know this, if I use this, then I can calculate W. 2V0 by W is E0. So as soon as I know my W, I also know my E0. So first thing I do is to evaluate W. W right now we may call W square. 2 into 11.8, 8.854 more existing, minus 14, pi square epsilon naught, 1.6 into 10 to the power minus 19. Then I give you bracket 1 upon 5 into 10 to the power 18 plus 1 upon 4.5 into 10 to the power 15 into 0.69. So I evaluated first V0, then I use that V0 and Na and D value to calculate W. Just substitute there all of it. This is twice Ks epsilon naught by Q 1 upon NE plus 1 upon ND into V0. I did this calculation and I get this is roughly 0.4449 or 45, sorry, W is 0.45 micron. So roughly for the bias not being applied, typical depletion widths or for the given kinds of doping will be order of half a micron, half a micron. Just to give an idea, this half a micron is how much? This length of a PN junction, typically we may call it say Wn and Wp, which is not W of depletion width, but the region where depletion doesn't exist, the neutral region. This will be of the order of 100 to 300 microns. So the depletion width is extremely small compared to the actual device dimension. So don't think that this 0.5 is big or small, it is much smaller compared to the actual dimensions used here. These values have some important relationship with something transport requirements. You will see why they have to be larger or smaller in two devices to use. So having shown that for a given PN junction, given any ND, I will be able to evaluate the depletion widths. If someone asks me what is xn0 and xp0, I can rewrite this expression. I know xn0 is equal to 1 plus nd by ne times w. Since I know ne nd, I also know w. So I will be, which will be less than w because nd by ne will be smaller. Therefore, sorry, larger. Sorry. It's the other way, is it? By 100. So it will be always less than W because xn0 plus xp0 has to be W. So you evaluate this xn0, which you will find may come something like this, 4, some further decimals. Therefore when I do xp0, I say W minus xno, so it will be 10 to power minus 4 micron. So that's what I was saying, if P diffusion, P doping is larger than N doping, the depletion width on the P side is much smaller compared to, it is order, don't say it is value, it's the order of this minus 3 minus 4 microns. So most of the depletion layer is going in the side of lightly doped region, which is N type in this case. So the calculation was done to show you that these numbers is very small compared to the actual depletion width. So many times in evaluation you may write xno is same as W, but don't say xp0 is 0 any time, because if xp0 is made 0, what will happen? The charge neutrality will not be available. Nd xno equal to Na xpo, that will violate, so which cannot be violated. Is that okay? So this issue that xp0 is normally very small if P plus junction, a P plus N junction is used. Contrary to this, if you have a N plus P junction, opposite may occur, all the depletion may go on the P side, nothing much on N side, reverse may. Is that clear? But if they are equal numbers, then what will happen? They will half on both sides. So that depends on the dopings are used, I may actually know which side is depletion going on or how much on left and how much on right of the junction, which I can always evaluate, provided I am given E and D and the temperature at which I am working. Now having done this, if someone wants to know E0 now, so how much is E0 from this formula? E0 is equal to 2V0 by W. So you can say 2 into 0.69P divided by micron volts, of course, by this one. W is how much? 0.45 and here you should write 10 to the power minus 4, this is micron, 10 to the power minus 4 micron, 10 to the power 4 microns is 1 centimeter. So this is all in centimeters. So you can say roughly this is 1.4 divided by 0.45, around 3, around 3. So this is around 3 into 10 to the power 4 volt per centimeter, around exact value. So the electric field is comparatively larger, 10 to the power 4 volt per centimeter is relatively larger, say kilovolts per centimeter. So even if you are applying no bias right now, even at the built-in voltage, the electric field is large enough. Is that point clear? This is why there is no carrier actually moving, because this electric field will actually stop diffusion as soon as the ions are exposed. This field will actually stop it. And that is why in equilibrium we don't see any current transfer. Now this fact that I can evaluate any of the quantities given can be used in designs. That is, given something, I will be told I want this, use these expressions to get that value, because you will be given answer at the end first. That's design. I want device to have so much capacitance, so much current voltage, at this voltage so much current. So you do inverse calculations to get those values. Is that correct? At that time, you may have to evaluate NA and ND yourself. You don't know which value. So what we do is normally we assume NA and D ratio for calculation, and then one value we decide, okay, we'll use this in for 16 or 15, correspond the other one we'll calculate by knowing the ratio. Or typically this doping is always higher, so we assume NAs in case of this doping. If you 10 to the power 19 kind of thing we put, you can assume that to be 10 to the power 19 and then evaluate what should be the N doping to make the device characteristic, which you started with. You say, okay, I want this. That's called design. This is what device simulators do. You are given a problem in which the spec is given. As a electrical engineers, this is analytical way to show how much value comes. But in reality, we will be given the final answer. Say, okay, do what to do. So many times there may be more than one solution. So you choose values may have reached the same result. That's your choice. That's your design. Because only those parameters you are looking which is coming into your spec, but they may influence something else. So at times you may have to again choose between, let's say breakdown then needs to be larger than this. Then one of the values will have to change again so that ratio remains same, but that value corresponds to breakdown. So there are tricks of the trade when problems are essentially different. That's how you call device design. There also will give how much I should keep this, how much I should keep this. This is part of design. However, why we don't do design first? Because we want to know how actually they come. So first we do analysis. Once we do analysis, we know which term connects to what. Then given that term, we come back and solve for the actual specs what we are doing. Of course, this course we are not really looking for device design. Those who will be in micro, hopefully so, latter continue to remain in micro and not shift to communication from DD side. For them, we may have another course of device design. At that time, we may show you how device specs are given, what is designed for that. Coming back to, this is a problem which I thought we should, this problem is only solved for the sake of numbers. However, as there is our person who told me capacitance, he is not here, that is not around. Okay, doesn't. He is preparing it. Okay. Okay, this figure is already there. Now I apply, let's say, minus potential here and plus potential here, which gives a total value of minus ER. If I apply negative potential to P and positive potential to N, this is called reverse bias, because P is positive and I am putting negative potential. N is positive and negative, but I am putting positive potential. So this is called reverse bias. If I apply reverse bias to this, what do I expect? If I apply, this is plus minus, already there is a built-in field here which is like this. Okay. This is our V built-in. Okay. You apply VR, which is reverse sense now. Since the direction for electric field is always from positive to negative, in any case, this external field, which is called field applied, you may say, also is in the same direction as the built-in field. Built-in field was also going from N to P. The applied voltage is also giving additional field to further enhance the field. If the electric field enhances, what will actually increase? That equation is still written. If this state increases, the voltage must increase. Voltage must increase. So if I show you a real graph for E, by increasing a voltage, I may have, this. As soon as you apply additional this, the area under the curve must increase. If it happens to do that, so this additional area is coming because of what? Additional voltage I apply. So let's say if there, instead of here we say the change in voltage is dV, there is the additional change in the charge here. QNAX W is essentially the charge. dV is given, there is a change in charge. However, by theory we know dQ by dV is capacitance. So as soon as I apply additional voltage, I am giving you a capacitive effect immediately because change in charge is proportional to change in voltage, which means there is a capacitance associated with this structure. Is that clear? So if I want to do this right now without going into too details, all that I need to know is, we know other day, capacitance is, this is a parallel plate capacitance structure, minus ions here, plus ions here. So there is an additional depletion width may now occur because you have applied reverse bias. So the width of the depletion layer now enhances, and if W enhances, what will happen to capacitance? Increase epsilon by W. Per unit area if I keep, then it is epsilon by W. So if W increases with VR, then my capacitance will go down. So larger the reverse bias I apply, smaller will be the capacitance. So where is the largest capacitance will get? Zero bias. So the zero bias. Because at that time the depletion rate is the minimum. Okay. So when I see plot voltage versus capacitance, by my thinking, simple thinking, this capacitance is called junction capacitance because it's a junction related capacitance. So somewhere here is the value of C0, and from here, if I apply reverse bias, I get something. Is that okay? So the capacitance goes like this. We'll calculate now how much is this capacitance variation. Once, if you know, there can be possibility that you can have this, you can have this, depending on the dopings you use. Okay. Which ones you prefer for tuner? For tuning purposes, capacitance variation, which will give me larger range of tuning. What should I do? Which one of the curves, let's say this is 1, 2 and 3, which curve you will prefer for a good tuner? Let's say, okay, my requirement is larger band I must cover. Okay. Which one? 2. So is that clear to you? So for a given application, the dopings are so adjusted that the bands are adjusted. Which band, where to where, which frequencies you want to tune this. In that case, corresponding doping, which will give W variation correspondingly, will be applied. Is that clear? Is the definition clear why dopings change capacitance? clear from here because Q contains QNAXD or QNDXN. Okay. Since those charges are going to vary with the voltage, correspondingly C will vary. So depend on those values, this slope should be different right here. That's how tuning or vectors or varigaps are designed. I am given, okay, I want from 1 gigahertz to 1.2 gigahertz or 2 gigahertz to 4 gigahertz or maybe 2 to 5 gigahertz. I am expecting too much bandwidth. It's 2 to 5 gigahertz is a huge bandwidth, 3-4 gigahertz is very large bandwidth. So in those cases, the capacitance should be such that I should be able to tune from left to right everywhere. The capacitance variation should be equal. Is that clear? So depending on what specs you are given on a vector, you have to make a choice of this. Let's do quickly what is capacitance. We say is Ks epsilon naught. This per unit area I am calculating. This is per unit area. Yes. Oh yeah. Look at the way it is. Your mobile is for GSM, so it has a band from say 880 to 890 megahertz. So I must at least have a bandwidth of 10 megahertz. But for Bluetooth, the Bluetooth has this is another way of transmitting. Bluetooth has a range from 2.4 to 5.4. Otherwise, I require so many tuners, 2.4 to 2.6, 2.6 to 2.8. So I require 12 and I must switch every now and then. Because if I am looking other band, I must into other RC circuit or LC circuit. Instead, if I have one LC circuit which tunes from this to this, I will solve my problem. Larger the hardware, what is the importance of larger number of hardware on each disk? Because the area will go secondly costly. Is that clear? For a lower cost, but they have their own problem. Think of it, if I have larger bandwidth, I may lose something. But I gain a lot of it because area in all handheld system is dominating. Because that you want to keep small as possible in that time, but cost will be proportional. You also want cost to go down because some Reliance mobiles are available at 1000 rupees. In that case, they will restrict ranges, they may put more numbers. They may actually have smaller bandwidth for each of them. Depends on what is spec given on a money, you can choose which one. This is how all the hardware is. Okay, so let's say this is, I am writing per unit area in all capacitance unless said otherwise. We use capacitance per unit area. Why? Because area is something device people finally will tell you how much current I want. So that area is decided not by just capacitance but also by current, because you will calculate current density there also. You will multiply by area to get your currents or power as they say. So area we normally initially don't use anywhere. The reason is further because this Q is charge density, charge per unit area. Is that correct? It's charge per unit area, so you will also get capacitance per unit area. So normally, unless specified, it is farad per centimeter square is provided. If I give you area, then you can as well calculate farad with many farad. Just to give an idea, and this is a function of PR. If you see this potential now from this graph, the V now, UV is V0 minus of minus. Two batteries, this essentially they will add. Both are in same sense, so the voltage on the battery will get added by applied voltage. Please look at it, I applied reverse bias, both fields are in the same sense. Okay. So they will actually add the voltage. Is that clear? So essentially saying, this was initial voltage, this is the new voltage, additional. So this is the actual difference you are getting, but since it is negative, it actually adds. In the case of forward bias, what will happen then? This will be V0 minus VF, because that is positive sign, so it will actually decrease that value. Is that clear? So the difference of voltage is additive or subtractive, depends on the sign of V of that. If this is so, then I can evaluate nu W at given value, which is twice Ks epsilon naught. Why? Let's say it is P plus N junction as it is, So what value I should write here? Let us say this is 10 to power 19 per cc and this is 10 to power 5 into 10 to power 15 of that kind dopings like this. So I can say this is smaller and then I can write V0 plus, that in normal cases VR is much larger than V. Reverse bias is tens of volts, 5 volt, in volt, 1 volt, at least more than 1 or 2 volts. So VR, which is typically V0 is how much? 0.6, 0.7 volts. So for analytical purposes you should write correct formula, but numerically you may say V is the net potential across the PN junction. You have increased the electric field, that means the voltage is higher, that voltage is V. You have applied additional voltage which gives me additional electric profile which increases W, so integral W is the V. Integral E dx now is V. So this additional V which you are getting, if it is larger than the initial V, means as much you apply is the voltage applied. Otherwise, if not so, you keep using these values as V0 plus. If they are not changing, put this one. But let us say this is 0.7 and this is 10, it is as much as 10. Otherwise, put 10.7, nothing great goes right or wrong. But since now I can say from here, if I write W, so CJD now of VR is Ks epsilon naught upon, write this value, 2 Ks epsilon naught upon QND V0 plus VR. If I do this above on this, so what should I get? This is under root Ks epsilon square, 1 Ks epsilon square goes there, so Ks epsilon 0 into Q into ND divided by 2 V0 plus VR denominator minus. This, what is this value? This is constant for a given junction. NDs are given, epsilon, Ks, everything is constant. What is varying? VR. So now Cj, I know how it varies with VR. That was the curve I was looking for, how Cj varies with VR. So by writing this expression, and which case I am solving right now? Abrupt junction. For other junction this formula may not be valid, you may have to change the formula. We will derive maybe linear unit soon. We will get what value we should get from this. If I do instead 1 upon Cj square, just written, it is 2V0 plus VR divided by Q Ks epsilon naught in D. If I do case Cj square, 1 upon Cj square this to the power half, sorry, no, 1 upon Cj square. Okay. So if I now plot this 1 upon Cj square against reverse bias, very interesting figure will appear. Call it V, okay, V means total. What is the curve will look like? Straight line. Where will it intersect? At the y-axis. What is this value? This is minus. Okay, this is minus value. So what is this value? V0 plus V0. So if I now plot 1 upon C square versus V characteristic for reverse bias, the intercept on the x-axis is essentially the built-in voltage. So when I check a diode, I measure its series capacitance and it's in a step junction. I will get measurement C versus V, C versus V. Plot 1 upon C square versus VR. As soon as I draw the line, intercept on the x-axis will now give me value of built-in voltage. And as I said, value is given by NA and D by NI square. NA is always assumed that this was too much. So NDs are known how much ND you would have been using for this device. What is the slope of this from here? 2 upon all that, Ks epsilon naught 2 ND. This is the slope of this curve. Yeah, this is x-axis is PR, reverse bias, sorry, total next PR. So this is the slope of this curve. So if I monitor the slope, what do I get calculated from that? Everything is known, so I actually calculate ND. So if I have a P plus N junction, I just, assuming it's step junction, hopefully most of them will be, then 1 upon C square versus PR curve will give me the value of ND. And if I know my ND, if I know my V0, I also know how much NA I have. So just one measurement can give you a lot of information. So that's how we do actually from, when you make a device, we actually monitor again and see what specs we wanted, are we meeting that. So this capacitance voltage, and now you can see from here, since this is the curve, C is proportional to VR to the power minus half. So larger the reverse bias, smaller will be the junction capacity. Obviously, because the width of the depletion there will enhance with increase of reverse bias, epsilon by W. W increase means C will go down. That's very simple. But this fact has to be remembered that this is only true for abrupt or step junctions. In reality, if it's not so, one has to evaluate the formulation between C and V once again and find from there, just to give a very great, this of course this will change some constant K, and this will actually come to the power minus 1/3. For linearly graded, we'll do it just now if possible. For linearly graded junction, this becomes 1/3. And for hyper abrupt it becomes 5/3, minus 5/3. So it depends on which device, which profiles you have. I can always get relationship between capacitance and voltage. And if I get that, I have a tuner element design. Is that correct? So application of a normal PN junction diode other than the one which we normally use in rectification or limiting or clipping, clamping, converting waves, wave shapes. This is another feature of diode. Integrated circuits. Please take it. All integrated circuits. What is the thing I said you in integrated circuit? How is different from PCB? In printed circuit board, you have a separate component. You have a capacitance, you have a resistor, you have a diode, transistor, separate. In integrated circuit, you have only one substrate, which is silicon in this case. So you must make all such components in silicon, created out of a PN junction. Capacitance is created out of a diode biased under reverse bias. So you have a diode sitting there, can act as a capacitor. All that is, you need a voltage which will decide what capacitance you want here. That's it. This is essentially how integrated circuit works, because all components must be made in silicon. Okay, so is that point clear? So a capacitance voltage is very crucial for many of the elements. There is something which I don't know whether this course should say. The directors can be used for generating what is called harmonic generators. They can also be used in what we call microwave amplifiers, lasers. There are a number of applications for this kind of capacity voltage characteristics. So this course just means that at least it acts like a good PV characteristics. Please remember, all these many things which we teach may have many explications than this course telling. Okay. Let's see now as I promised you, we will do something more about the linearly graded junction. We may not fully derive it, but at least show you what is that, how it differs, why is it relevant. Actually, step junction and linearly graded junctions are some way closer to the real life profiles I can create, which may come closer to one of them. Okay, and therefore these two cases are normally handled, extreme cases, step junction and linearly graded. So most profiles can be in the two. Okay, so here is a profile I want to show you. This I am plotting ND minus NA versus X. This is called linearly graded. This is called linearly graded. That is ND minus NA on the my, this is my X is equal to 0. So to the my left of this, ND minus NA varies linearly with X. So I write with the same slope, ND minus NA increased on the inside. What does this mean? It's becoming N type. What does this mean? It is becoming P type. Is that correct? But it has a gradient throughout. Let us say for some reason at zero bias they reach a value of xp0, xn0 and after the same process some carriers going from P to N, some carriers going from N to P, ions are exposed. So this is again what is the condition I should hold always? Charges to the left must be balanced by charges on the right. Neutrality must hold. This is called linearly graded junction. So what should I write? Yes? No, this will continue. Yeah. Profile is there, but only these many are essentially exposed because of the concentrations which gave what slope you are giving. Only these, like in a normal step junction, only certain amount of ions it will create some field. Once that field is reached, no more diffusion, so it will stop. I repeat, in the case of step junction, what did we say? As soon as I brought P and N together, holes from P went to the N, opening the acceptor. Electron from N went to the P, opening donors. Same thing happened. Even in this, electrons went from N to P, holes went from P to N. All that it has a profile, so the ions will be in that profile only. Is that correct? And the slope is called A. Slope of this curve is A. So it's called grade constant. The dN by dx is A. If that is so, let's write an expression d by dx. Yes, now what should I write? At least in the range of, okay, now one interesting feature. How much will be xp on, how much will be xn? Will they be same? They will be same because half of the, it's the same grade constant. So one can say xpo is equal to xno is W1. So net W is half on the left, half on the right because it has a linearly grade going on. Linear always is equal. If not linear, then it will not be equal. If that is so, d by dx I can write as q upon ks epsilon naught a into x. This is linear slope. Y is equal to mx. Y is equal to mx is the relation. So I wrote that. So what do I do now? I integrate it again. What for? To get Ex. If I know Ex, then what do I calculate? V0 which is integral e dx. Or is it clear? If this is my differential equation, I integrate once, but what will happen to x? It will become x square by 2 plus c. When I calculate voltage, what will happen to that? It will become q minus x kind of term, and that cube term, that expression I was writing there, you see 1/3 that cube is appearing here, so we will write down. So okay, so this equation we essentially say minus w by 2 x w by 2, this equation is valid. I have evaluated, just write down final answer. Ex, I differentiated this, I get qa upon 2 ks epsilon 0 x square minus w square by 4. This is my Ex. If I differentiate this, and what is the boundary condition I should apply? At x is equal to w by 2 or x is equal to minus w by 2, Ex is 0. At x is equal to w by 2 or x is equal to minus w by 2, electric field ahead is 0. With this expression you see, what kind of shape do you expect here? What kind of shape you expect from here? What is this? Parabola, x square, it's a square term. Okay. So essentially the electric field profile is parabolic now. There was triangle, now it is parabolic. Is that clear? So for linearly graded junction, again you can find E0. What is E0? Just substitute x is equal to 0 here. So I can get E0 is QA 2 ks epsilon naught minus w square by 4, or QA w square upon 8 ks epsilon. So this is the maximum electric field in linearly graded junction. Is that correct? What is the shape? Paraboloid, square law. So it's following a parabolic relationship, and the maximum field is, what is A? The linear grade constant. So whatever slope is given to you is the grade constant. What is the unit of this? Should be A. जरा समझाओ मुझे. Per cc per centimeter 1 by cm4, is that correct? Per cc by cc centimeter is per cm4. So unit of grade constant is per centimeter to the power 4. Okay. This is the unit. So you must correctly write units. If you feel you are not doing correct, then please check again. Okay. So what do I now want to calculate after this E0? V0. V0 is integral E dx. I can say minus w by 2 to 0 and 0 to 2 w by 2, but they can be double of that. Okay. So is that clear? Since w by 2 is same as this, so minus w by 2 to 0 and 0 to w by 2 is just twice of one of them. So if I do this, which I did, I'll just give you the expression for you. V0 is QA W cube upon 12 ks epsilon 0, or W is 12 ks epsilon 0 V0 divided by 2a to the power 1/3. So now depletion layer goes, if I apply reverse bias, where do I add that additional value of V? W at any other V, VR of course, reverse bias is 12 ks epsilon naught upon QA V0 plus VR to the power 1/3. So I can find now the depletion width enhancing as cubic law, okay, 1/3 kind of law it will follow. So now if I calculate CJV, which is epsilon S by WV, 1 upon WV is how it will show, that means it is proportional to V0 plus VR or just VR by 1/3. Earlier what was the formula given here? Half. Step junction, this was half. In the case of linear relay, it is 1/3. So what is it, faster changing or slower changing? Capacitance with voltage changing lower way or faster? पहला था इसको 1/3 डायरेक्टली लें, so VR to the power minus 1/3, and in step junction it is this. This is faster. Faster means for the same VR, which one will have larger capacitance on the capacitor? Larger VR. तो कम होता है या ज्यादा होता है? कम होता है ना, क्यूब रूट कम होता है, इसका मतलब ये यदि कम है तो कैपेसिटेंस ज्यादा है. So you are looking for those characteristics. You see that? So for the same VR, the upper one will be linear degree, lower will be abrupt junction. Is that clear? So you are asking, you must have thought, how do I go about? One way is to change NAND, the other is have a linearly graded junction, in which case you may have slower variations as you are. Is that clear? These are way the designs are provided. You want this, okay, you make this device. Or if you are using this device made by someone, catalog लो और सब डायोड का कैरेक्टरिस्टिक देखो क्या दे रहे हैं, जैसा भी आपको चाहिए to pick up one of them for your circuit. Is that clear? Inversely saying, I don't know whether they still have YY. They have. You don't have YY every day. No? Okay. No, it has advantage, disadvantage both ways. Okay. So I can. Is that point clear? A PN junction is a good capacitance voltage device. What did I promise in the every device? Which two electrical property characteristics we will always find out? For every device, I will write this relationship first. And what is the next relationship I want? For every device, I want to know the capacitance voltage relationship and current voltage relationship. Then I can represent it as some equivalent of that, and I'll say I'll solve it now. So one I have done. So let's start with the transport, IV, because we want to know what is current voltage characteristic, which is more dominating than CV. CVs are specific use. IVs are required everywhere. And I already said you, typical IV characteristics of a diode. Yes. पहले IV कर लेते हैं, फिर देखते हैं कि कैपेसिटेंस क्या होगा फॉरवर्ड साइड. होता तो कुछ नहीं. There are two capacitors are there. One is called diffusion capacitor, other is junction capacitor. Diffusion will dominate, so junction will go. So, थोड़ा सा बताएं. You are right. I think you have preempted my. He is asking me that I have always talked of reverse bias. Why I never talked of bias? The problem is, as soon as I will apply forward bias, something else will happen. And that the capacity effect will be much less. Or to say that R shunting this C will not be as small, as large. Equivalent of a diode, I already said, is this capacitance shunted by this R. In reverse bias, this R is close to infinite, very large, 10 to the power 6 to 10 to the power 7 ohms, tens of megohm to hundreds of megohm, depending on the saturation we have. This capacitance 1 upon j omega C is smaller than R. When I go into forward bias, R will be smaller than Q, because C is essentially actually enhanced, and R will be much smaller than that. So that C effect in forward bias, of course it has. I am not denying that. But I thought first let me do IV, then show you how much R I am getting. Why I neglect the capacity. This is called preempting. So you have preempted me, but let's see. Okay, I see this characteristics, and in the reverse bias, I find constant current. So if I want to find this relationship, आगे क्या 2 minutes हम फंडा मार देते हैं. Now please remember, at zero bias, actually we are not short circuiting, but I said even if you short circuit, no current flows. This characteristics tells so. V is equal to 0, there is no current. But normally when I take a case V is equal to 0, I open circuit and say there is no voltage externally. Is that clear? Normal diode just now I did, I say no voltage applied. But even if I do this, which is also V0 applied, it still gives me a 0 current. Think of it why. Whereas battery get discharged, diode doesn't. Something is there. Think of it. Anyway, but the actual current is 0 at 0 bias. In 0 bias or open circuit, what we said, the PN junction Fermi levels are somewhere here. If I join, then this is my conduction band. Sorry, it is P, so Fermi level is here. Fermi level is same in the case of the other device inside. This is ECP, this is EVP, this is EFP, this is EFN, this is ECN, this is EVN, and I get, if you want halfway also, PI also is half. Then we said when I join this, I create a potential barrier of value V0. In 0 bias, I say it creates a potential barrier of V0. Now we want to see if I apply to a diode the bias. This was my initial PN junction. Yes, 1 minute. So as soon as I apply bias, what will happen in the reverse bias? What did I say you? The bias added to the built-in voltage. If I apply reverse bias, a forward bias, it should subtract from this. If it subtracts from this, let's say in the case of forward bias, what does this going to tell you? The barrier height is reduced. So what is physically it means for you? Now electrons find lesser height to climb. Holes find lesser height to climb. So they are started diffusing again. Is that correct? Initially there was no carrier motion. I connect forward bias, I find barrier reduced. So holes from P started moving towards N, electrons started moving from N towards P, and since there is a battery terminal, these carriers will be collected and current is maintained because battery can keep doing charging. So a forward current can flow as soon as I apply forward bias. If I apply reverse bias, what will happen? This barrier will further increase. So unlikely that it will climb. The probability of climbing is much smaller. Very small current which anyway was existing also continue to flow, almost negligible. This characteristic comes from bands. We'll see next time, band bending for the bias.